So we have this experiment where we have 0.016 microcurie of a phosphor sample that is injected into a medium that contains a bacteria culture. And after 1 hour, the cells are washed, and the 70% efficient detector reads 720 counts per minute from the cells. And the question is, how much of the radioactive phosphor did they absorb? And first of all, in this problem, since it's only after 1 hour, the decay time or the half-life of the phosphor is much longer than 1 hour. So we assume that no decay has yet happened. So the activity is the same as the original activity, and we start by calculating that activity. And we use the 0.016 microcurie, which is 1.6 times 10 to the minus 8 curies. And then the next factor, the 3.7 times 10 to the 10, is the conversion from curie to becquerel. And so we have 592 becquerels, or disintegrations per second. And the counter, therefore, should read 0.7 times 592 becquerels, which is 414 counts per second, if all of it was absorbed. That would be 24,900 counts per minute. However, the counter reads 720 counts per minute. Therefore, the ratio of the 720 and the 24,900 is the fraction of the phosphor molecules that have been absorbed. And that corresponds to 2.9%. So 2.9% of the phosphor has been absorbed. And that can be measured using this technique. So today will be mostly about application of radiation. So the most straightforward application of radiation in medicine is radiation therapy. You use radiation to destroy unwanted tissue, meaning cancerous growth, or benign tumors as well, but usually it's not necessary there. And this is particularly effective because cancer is defined as an uncontrolled rapid reproduction of cells, and such cells, when they're reproducing often, they are particularly vulnerable to radiation damage, a bit more so than healthy cells which don't reproduce as often. However, it does kill healthy cells as well, and radiation therapy often induces radiation sickness in the patient. And so it's a balancing act. Usually one therefore tries to not irradiate the entire body, but just that part of the body where a particular tumor is identified. And moreover, one usually varies the path of a beam of radiation to limit the damage to the healthy surrounding tissue. Only the tumor is always irradiated, surrounding tissue is only irradiated part of the time. The radiation that is needed for this therapy can be generated, for example, with an X-ray beam using accelerated electrons between 200 keV and 5 MeV. And also one can use protons, neutrons, and electrons, and even pions from accelerators. Or one can use a radioactive source such as cobalt-60. If the source is small enough, one can place it inside the body for targeted, localized destruction of the cancer. And yet another alternative is if the tumor is in an organ that absorbs a certain type of chemicals, then one can use a radioisotope in those chemicals to target the destruction. A perfect example of that is the usage of iodine-131 to destroy cancer of the thyroid. An additional benefit in this case is that the thyroid tends to absorb the iodine, in particular in regions where it grows abnormally. So therefore it is more targeted than it would be otherwise. Another good candidate are proton beams, and that is because proton beams, they deposit their energy unequally along their path. So usually there's a region where you get uniform energy deposit, and then after some distance, almost all the energy is deposited in one go. And where that distance is depends on the energy of the protons. So therefore one has sort of three-dimensional control where the radiation damage occurs, and it works so well that due to the physical size of the tumor, you actually need to have a proton beam of several energies. Otherwise you wouldn't destroy the entire tumor. Unfortunately, proton therapy requires large accelerators, which are expensive, so until recently only a few hospitals were using them. Another medical benefit to radiation is one can use so-called radioactive tracers. That means you replace normal non-radioactive isotopes with radioactive ones. And if you do that in the right substances, then because the radioactivity acts like a paint or a tag of those kind of atoms, they can be then traced through the body using Geiger or scintillation counters. And a very good example is using carbon-14 or tritium to check, for example, how food molecules are digested and where they are transported. So one can make things like this autoradiogram of a leaf using carbon-14, for example. Or on the bottom you can see replicating DNA. In other words, such tracers can also be useful for research. One can determine how amino acids are synthesized or study cell membrane permeabilities or other such things. When they are used for diagnostic purposes in medical science, one usually uses an isotope called 99 technetium. And it's a metastable state of technetium, meaning that it emits a gamma with a half-life of about 6 hours. And it's formed when in the beta decay of 99 molybdenum. And it combines with many compounds, and so by choosing the right compound, one can use it as a tracer in many different organs or regions of the body. And usually a single gamma detector is moved across the body. However, one can also use a gamma camera and take a picture at once. And in the case of such a camera, one can even make movies, meaning time-dependent pictures. And those pictures are called scintigrams, where scinti stands for the scintillator. For medical imaging, a lot of progress has been made using the so-called tomography technique. So in classical X-rays, all you get is a shadow image. So you have your X-ray source, and it shines through the body, and you have a film on the other side of the body, and it leaves a shadow, or depending on how much of the X-rays were absorbed by the different density of the tissue. There's fairly little diffraction and refraction. So it's only absorption and scattering that makes the picture. In the computed tomography, tomography comes from the word tomos, meaning sharp or slice. One uses instead a collimated beam, meaning that you pass the X-rays through some hole, like in this picture down there. And this collimated beam is then detected with a collimated detector also, and so you get only an image in a well-defined direction at a well-defined position. And then one takes many angles and positions and then computes an image one slice at a time. And this technique is also abbreviated as CT or CAT, where CAT means computerized axial tomography. While it's possible to proceed this way with a single detector, it is not particularly useful because it would take a long time to take all the images of all the angles and so on, and the patient would become impatient probably. One typically with a fast scanner typically uses a so-called fan beam, meaning that you generate the X-rays on one side of the patient. So the patient is lying down here. And so you generate a beam that fans out in many directions, and you have an entire array of detectors that take the picture. And then you rotate the whole assembly around the patient to get the different angles. If one wants to take pictures even faster than that, because this is sort of limited by the speed with which you can rotate this assembly around, which is quite heavy, you can have an entire ring of detectors, and you generate X-rays by having an electron beam that is then scanned across a target, which also surrounds. So instead of rotating the X-ray source, you just scan an electron beam across a target that surrounds the patient from all sides. And it only generates X-rays at one instance from one part of from one direction only. And it's much faster to scan beams than to mechanically rotate. So those are called fixed source machines. The analysis of tomography, how to generate the picture, is mathematically somewhat involved. However, the principle is relatively easy. You logically define pixels for your image, meaning square pieces of the body from which you want to determine how much X-rays were absorbed by this particular pixel. But you have, the measurement you have are projections on various axes. So let's say we have the absorptions 2, 4, 5, and 9 for 4 pixels, and we take 4 angles. So in angle 1, we get the sum of the left pixels, 2 plus 5, and 4 plus 9 on the right-hand side. For angle 2, we get 2 plus 4 at the top and 5 plus 9 at the bottom. And then for angle 3, we get the diagonal, or 2 plus 9. And for angle 4, we get the other diagonal, or 4 plus 5. And then one uses mathematics to reconstruct the original numbers 2, 4, 5, and 9 from those measured values. And this technique works in 3D also, so one can actually assemble 3D images. And the more detail one wants, the more scans are required to have enough information to actually reconstruct the image. And the image is often shown in false colors to emphasize particular features, like this particular area in this brain. And one can apply it to ultrasound and radioisotope emission tomography as well. And then finally to the magnetic resonance imaging technique, which we will talk about later. So for the emission tomography, one uses a tracer as a source rather than an X-ray, meaning you make the body itself glow. So you then detect and compute the image as with a CT. One only gets one slice this way, though. Usually one uses gamma emitters as the tracer because gammas are transported the easiest out of the body. So this is called a single photon emission tomography, or SPET. And on the top you see a scan of a brain with a particular brain disease as a sample. Another very useful technique is to use positron emitters such as carbon-11, nitrogen-13, oxygen-15, or fluoride-18. And the idea there is that if you have positrons emitted, they don't go very far. So you have the positron, it travels for a short distance but not very far, and then it encounters an electron and it annihilates, and it makes two back-to-back photons. And so you have detectors surrounding the patient which look for simultaneous detection of two photons that are back-to-back, and that gives you the axis among which those photons propagate. And you then make an image using the tomography technique. You then proceed in the normal way. And those are called PET. One particularly interesting technique uses magnetic resonance. And to talk about magnetic resonance, we first need to talk about particle spin. That's something we haven't covered so far. Particles, like the electron, for example, have intrinsic angular momentum. And this is called the spin S. And this intrinsic angular momentum is just like any other angular momentum, is quantized. And particles either have spin 0 or spin h bar over 2, or spin of h bar, or 3 times h bar over 2, or 2 times h bar, and so on. The magnitude of angular momentum or of spin, the magnitude square, due to the weirdness of quantum mechanics, is not just spin times spin, but it's actually spin times spin plus 1. So if you have, say, a spin h bar over 2 particle, then it has the magnitude square of h bar over 2 times h bar plus 1 over 2, or 3 times h bar square over 4. The z component of the spin, angular momentum is a vector, ranges from minus s to plus s. So for example, for h bar over 2 particle, from minus h bar over 2 to plus h bar over 2. And the x and y components in quantum mechanics don't exist simultaneously with the z component, because the uncertainty principle makes them maximally uncertain. If you measure the z component, then x and y don't exist. If you measure the x component, then y and z don't exist. Spin is tied to magnetic moment, and that sort of gives it the name, because if you imagine that the electron is actually a little blue ball, even though it's not, that is spinning around its axis, the electron is charged, and so you have charge spinning around, and that sort of is similar to a loop current. And a loop current produces a magnetic field, a dipole field, and that can be quantified with a magnetic moment. Since the angular momentum or the spin is quantized, the magnetic moment is also quantized. And in the case of the electron, one defines the Bohr magneton, or the quantum of the magnetic moment, in a similar way as the Bohr radius was used to quantize the radius. And it's given as EH bar over twice the electron mass. The quantized magnetic moment, the magnetic moment is quantized in units of the Bohr magneton, but if we want to get the relation between the spin and the magnetic moment, it is not simply mu equals s over h bar, but there's an extra factor, the so-called gyromagnetic ratio. And that factor is, for electrons, is approximately 2. So once we have a magnetic moment, which we can calculate from the spin, it has an energy in a magnetic field. And the energy classically of a magnetic moment in a field, there's magnetic moment oriented this way and magnetic field oriented that way, and there's an angle theta between them. And the energy is given by the size of the magnetic moment, the size of the magnetic field, and the cosine of the angle between them, and a minus sign. The magnetic field singles out a particular direction in space, and that defines the z-axis of the spin. So if there's no magnetic field applied, then the spin could point in any direction because it's not measured. But if you apply a magnetic field, then one particular direction is identified, and that is usually then called the z-axis. Examples for particle spins, in case you have heard recently, the so-called Higgs boson was discovered in Switzerland. And that is actually the first fundamental particle that has no spin at all. And that's the particle that makes other particles massive, or it is the quantum of the field that makes other particles massive. So the electron, the neutrino, the quark, the neutron, and the proton, all of those have a spin h bar over 2. The photon and the gluon, where the gluon is the quantum of the strong force, just like the photon is the quantum of the electromagnetic force, it has twice as much spin. It has spin of h bar. However, because the photon is massless and so is the gluon, one of the z components doesn't exist. You can't have the z component of the spin being 0. It can only be plus h bar or minus h bar. For the W and Z bosons, and those are the quanta of the weak force, it also has a spin of h bar, but all three components exist because those are massive. Then finally the graviton, that is the quantum of the force of gravity, it has a spin of 2h bar. In general, all the bosons, remember particles can be either be bosons or fermions. All the bosons have integral spin, and all the fermions have a spin that is an odd number times h bar over 2. So much about the spin. Now about the magnetic moment. For the neutrino, we don't know what the magnetic moment is. All we know is it's small. It's less than 10 to the minus 10 in units of Bohr magnetons, where the electron has 1 Bohr magneton. So for the electron, this gyromagnetic ratio is 2, and since the spin is h bar over 2, 2 2's cancel, and the electron magnetic moment is just 1 Bohr magneton. For the proton, this ratio is a very complicated number. It's about 2.7928. And the spin is also h bar over 2. And we then define a similar quantity as the Bohr magneton, but we replace the electron mass with the proton mass, and then it's called nuclear magneton. And so the proton has a magnetic moment of 2.7928 nuclear magnetons. Then the neutron, even though it's electrically neutral, it still has a magnetic moment, and it actually has a negative gyromagnetic ratio, which means that magnetic moment points in the opposite direction as the spin. And the ratio is minus 1.9135. And because it has a large magnetic moment, it must mean that the neutron has structure. It can't be a fundamental particle. And indeed, we think that it consists out of the 3 quarks U, D, and D. If we now see what happens when we expose a nuclear spin, and since the nucleons have spins, the nuclei have spin also. They don't have to have spin, but certainly the hydrogen nucleus, which is just 1 proton, will have spin. There are 2 possible states. The one where the spin is aligned with the magnetic field. This is usually called up. And the other one where they're anti-aligned, which is usually called down. So then there is an energy difference, just like for the classical magnetic moment, between up and down. And that energy difference is the extreme case between cosine theta of +1 and cosine theta of -1, or 2, times the size of the magnetic moment, mu p, times the magnetic field strength, B. And so because of those energy levels, and those energy levels are proportional to the magnetic field, that means that we can define the size of the transition between them. So just like any other energy levels in atoms, you can have electromagnetic transitions or electromagnetic radiation that carries the nuclear spin from one state to the other or back. So it's kind of like defining your own energy levels in your atom and controlling it by the magnetic field. And that is what is meant by magnetic resonance, nuclear magnetic resonance. So since we can have transitions between those energy levels, and we can actually calculate the frequency of the electromagnetic wave that is required to make this transition, since this depends on the magnetic field, which consists out of the applied external magnetic field, and those that is produced by nearby other particles, such as electrons and other nuclei, we can then control the actual resonance frequency, which is simply magnetic field divided by h times twice the magnetic moment of the proton in the case of the hydrogen nucleus, for example. And then one gets this formula that the resonant frequency, where those energy levels can be changed from one to the other, is 42.58 megahertz times the external field in units of Tesla. And that is true for free protons, like in the hydrogen nucleus. So if the protons are bound, then it slightly detunes to a different value. But 42.58 megahertz for 1 Tesla field is in the radio frequency region of the spectrum, and that is particularly useful because we have lots of radio frequency technology to detect such radiation, and it can pass outside of the body when it's produced in the body. So as an example, let's actually calculate this formula. So let's calculate the magnetic resonance frequency of free protons in a 1 Tesla magnetic field. And so first we get the magnetic moment. So that's this funny number, 2.7928, the gyromagnetic ratio, times h bar over 2 times the proton mass. And that is h over 4 pi, the proton mass, since h bar is h over 2 pi. Since the frequency is the energy difference over h, or twice the magnetic moment times the magnetic field divided by h. And if we now plug in to the formula for the magnetic moment that is just above, then we get 2.7928 times the elementary charge times the magnetic field divided by 2 pi and the proton mass. And if we plug in numbers for that, then we find out it's indeed 42.58 megahertz for a 1 Tesla magnetic field. Now we can actually apply it for magnetic resonance imaging. So we control the energy levels by the field strength. So for example, we can have a non-uniform field where different parts of the body are in a different strength magnetic field and therefore have different resonant frequencies. So that is one way to localize where the radio frequency is coming from. Or one can excite all the hydrogen nucleus by hitting them with one radio frequency in the entire body, and then before they de-excite and then emit radio frequency, you change the field into a non-uniform one. And that is the most useful technique. So you first apply a uniform field. And you get two particular energy levels everywhere in the body. And so all all the nuclei are driven into the upper energy level. And then in the step 2, you change the, and so that is the case everywhere. And in step 2, you change the magnetic fields, therefore those energy levels will change depending on position. And all the upper energy levels are filled, and they fall down and emit different different radio frequencies depending on where they are in the body. And then you can use the tomography techniques to turn this into images. This technique of first exciting and then waiting for them to decay, that's called spin echo, because it's kind of like you hit it with radio frequency, and then a short time afterwards, radio frequency is coming back like an echo. And it gives you resolutions on the order of millimeters. That means it's not so bad compared to other techniques. So a conventional X-ray can give you resolutions up to 0.5 millimeter, or a CT scan can give you 0.5 millimeter. And nuclear tracers will give you 1 centimeter typically, for example, the SPET. And positron emission will give you 3 to 5 millimeters. And the MRI can be pushed up to 0.5 millimeter. Ultrasound, by the way, gets you about 2 millimeters. But one great advantage of the MRI is that the radiation is radio frequency, so it's not ionizing. That means it is harmless to the tissue. There's no radiation exposure. At the very end, let's talk about other types of nuclear reactions. Nuclear decay is only one type of reaction. For example, even Rutherford himself observed that some of the alpha particles are absorbed in nitrogen gas and protons are emitted. And one can understand that with this nuclear reaction, that the helium interacts with the nitrogen and it makes oxygen 17, and 1 proton comes out. And sometimes one uses short notation like for the other nuclear reaction that we already encountered, where carbon-14 is produced in the atmosphere out of nitrogen-14. And so this notation just means the same thing as neutron plus nitrogen is carbon plus, gives carbon plus proton. And just like we had Q values for the nuclear decays, we can define Q values for nuclear reactions using the masses of the particles before and after. If that Q value is bigger than 0, then you have exothermic reactions, and otherwise you have endothermic reactions. So it's pretty much the same thing as in chemistry, basically. And to balance the reaction equation, you have to conserve energy, momentum, angular momentum, charge, baryon number, and lepton number. Let's just look at one brief example. Let's say we hit carbon-13 with protons, and out comes nitrogen-13 with neutrons. Can this happen if we bombard carbon-13 with 2 MeV protons? And can it happen when we bombard it with 3.5 MeV protons? What we do is the same as for the decay. We look at the masses for carbon-13 and for hydrogen-1,1. So before we have the reaction taking place, we have 14.01180 atomic units. And afterwards, when we just have the nitrogen-13 and the neutron, we have actually slightly more mass, 14.014404 units. So you would say, well, that means the reaction can't take place, but it's not true because we have an extra 2 MeV from the protons that we need to take into account. So if we look at the mass difference and we convert it into energy units, we find that it corresponds to 3 MeV. So since we have only 2 MeV, the reaction cannot take place. But it can take place if we have 3.5 MeV. Actually, it probably doesn't take place even for 3.5 MeV because you have to overcome the Coulomb barrier in this case. And so it requires an extra activation energy, and 0.5 MeV is unlikely to be enough. But at least it is possible that this reaction takes place for 3.5 MeV protons. Fermi was the first to realize that for nuclear reactions, neutron bombardment is a useful technique because you can avoid the Coulomb repulsion or the Coulomb barrier, and it is therefore more effective to trigger nuclear reactions. And he produced many new isotopes just by bombarding known isotopes with neutrons and making new ones out of them. And he also realized that you can generate new elements by bombarding the heaviest element, which is uranium, with neutrons. For example, you can produce neptunium and plutonium by neutron bombardment of uranium. And people in Germany, following on his studies, they discovered that you can actually blow the nucleus into smaller pieces by bombarding them with neutrons of the right kind. And that is called nuclear fission. So it's different from nuclear decay because large pieces come out, like a krypton nucleus, for example. Let's talk about nuclear power in the last few moments. And nuclear power sort of recently has gotten a bad name, but I think we should all like nuclear power because we can only exist with nuclear power. Stars like the sun provide constant supply of energy over long periods of time only because they are powered by the nuclear fusion of light nuclei, which is a form of nuclear power. And interestingly, for that fusion of light nuclei in stars like the sun to take place, you require the strong and the weak force for the nuclear processes. You also require the electromagnetic force to transmit the energy, and you require gravity to hold the star together. So the star begins nuclear reactions by making helium-4 from hydrogen, which is just a single proton. And the question is, where does the star get the neutrons to make the helium-4, because helium-4 has 2 neutrons. So to make neutrons, the star has to convert protons. So we need to make neutrons out of protons, and that violates charge. So therefore, we either have to emit a positron in the reaction, or we have to absorb an electron. And then the charge will be conserved. If we absorb an electron, then the electron plus the 2 protons have charge 1. And so does the outcoming deuterium. So, however, that runs into another problem, that nuclear reaction, because we also have to conserve the lepton number. And if we emit or absorb an electron, then we have changed the lepton number. And so that problem can be solved by emitting a neutrino or absorbing an antineutrino, but emitting a neutrino is easier. So that means that we have 2 possible basic reactions. Proton plus proton goes to deuterium, H21, plus positron plus neutrino, or proton plus electron plus proton makes deuterium plus a neutrino. The first process is called the PP process, and the second one is called the PEP process. And then once you have deuterium, you can fuse it with another proton to make helium-3 plus a gamma. And then 2 such helium-3s can fuse and make a helium-4 plus 2 protons. And the star can then generate energy that way. So in sum total, we have 4 hydrogens that make helium plus 2 electrons plus 2 neutrinos and plus 2 gamma rays, and it releases 26.7 MeV in that entire process. So there are other reactions that can also happen. For example, you can make beryllium-7 by fusing helium-3 and helium-4. Or you can even make boron-8 by fusing another proton to the beryllium-7. And all those processes, they were figured out by Hans Bethe, who received the Nobel Prize for this work, and Carl Friedrich von Weizsäcker for different types of processes. The first one to suggest it was Arthur Stanley Eddington, but he did not figure out how to make the neutrons. In particular because when he suggested it, the existence of the neutron wasn't known yet. This first process of making neutrons out of protons is important because it requires the weak interaction, and that means the process isn't very likely to happen. And for that reason, stars don't just explode in a split second, but burn over millions of years. So it's rather important that there's a weak process involved. Finally, once all the hydrogen is exhausted, then the star can produce energy by fusing helium. So, for example, 3 helium atoms can become 1 carbon atom. So if we summarize those processes like this, the process on the left is called the PP chain, and this is how our sun generates energy. And then there's a second cycle, catalytic cycle, called the CNO cycle, which hotter stars produce their energy with. But in both cases, hydrogen is burned into helium and energy is released. And this triple alpha reaction, where carbon is produced out of helium, is in the older stars. And there's actually direct proof of this PP chain process, because the neutrinos that are made in the reaction, they are very penetrating. They can even get out of the core of the sun. And they have been measured on Earth, first by the pioneer Ray Davis. And this is the energy spectrum of the 8 different types of solar neutrinos that ought to exist. And out of those 8, 3 different species have been uniquely identified. There's no direct observation for the CNO cycle so far, but you can infer it from the sequence of stars observed in astronomy. So let me finish here, and I will summarize this chapter on Friday. Thank you for your attention.